Hello everybody, my name is Šimon Prokop. I'm working with Lukáš Kurila, he's my tutor, and I would like to show you something about simulation-based parametric models of lightweight structures. It's a topic we came across while discussing design of these shapes, because it can get quite tricky when you don't have the tangible experience with building a grid shell or something like that. And in order to make those structures work properly, you really need to get the shape exactly like it should be. And I think it's quite amazing that the tools we have today available are so powerful that they can teach us or give us this experience with these structures, and we can learn how those structures work, how they behave, and we don't have to cut any pieces of wood for that. And then when we go to design, we are quite confident that these things will work in a certain way. So I'm just going to show you these things in a design environment which is called Grasshopper. It's a Rhinoceros plugin which is meant to do parametric modeling. So we're going to be exploring some scripts here in the canvas, and we're going to see the result of that script here in 3D view. So I would like to start with this catenary curve thing. Thank you, Aleš, for this nice image of hanging chains, and also thank you for inviting me to talk here at this cool conference. I believe that everybody knows this catenary curve, but yeah, there's a mathematical equation for that. It's a cosinus hyperbolic of a t over a. Of course, we might know this curve more from real world whenever we have a chain or something with little pieces connected, and it hangs in the gravitational pull of our of the Earth. It usually forms one type of this shape, the catenary curve. So let's jump into Grasshopper and let's see how we can model such a thing. So example number 1, a catenary curve. So I'm using this plugin called Kangaroo, and I'm just going to quickly explain what can you see here in this short script. So we have 2 points to start with. There's a line in between them, and we take that line and divide it into many points. It can be as many as we want. As many points, the more points you have, the more detailed the simulation is. And then we have to create these little segments. So we had points, and we connect them with a line, and there's like many lines here. So these 2 points are connected with a small line, and these 2 points are connected with another line, and these 2 again are connected with a line, and so forth. That means we have something like a chain, right? It's many pieces connected together, and that's something we call a spring. So in here you can see that this goal object is named goal.spring. That means it's something which can extend, and it can stretch, and it can get shorter or longer, and that's something which allows us to do this, find this equilibrium state where every single one is stretching just enough to accommodate for the other forces in the system. As I'm talking about other forces, as we have all those points, we can apply some vector. Since we are interested in gravitational pull and hanging chain, I'm pointing all the vectors downwards. That means there's a force acting on every single point here. That's another goal object for our solver. And the third thing, very important, if I kept it running without these anchor points on the edges, the whole simulation would just drop down and everything would disappear. So I need to anchor it somehow, and that's another type of data here, goal.anchor. So with all these things being said, I can just go back to normal pink preview, and let's run the simulation. So I just double click here, and here we go. we have this nice curve dropping down like this. Obviously you can see that it's a catenary curve, and if I restart the simulation, you can see that it bounces back and forth until it comes to a, as I said, equilibrium state. Then actually no more iterations are needed, and this little message that the whole simulation converged to a stable state is displayed, and it's usually something around 2700. Like for this case, it took like 2760 iterations. The funny thing is, since this is a tension only concept, right, there are only little springs being tensioned. They are enlarged, like they're getting longer. If I switch the gravitation to the other side, this is a situation where such an object would be compression only, right? Because now it's not tension, it's compression. So quite simple, quite simple script with just 3 elements: the springs, unary forces, and then anchoring on the edges can give us already some kind of idea about compression and tension only structures. Okay, cool. So that's a catenary curve. Then I'm going to show you this image, and I'm again going to assume that you know that Sagrada Familia had this cool model done by Antonio Gaudi, where many ropes were hanged from the ceiling, and many sand bags were put on these ropes to actually simulate the shapes of vaults. And that's exactly what I was talking about. If it's hanging down, it's tension only, but if we switch the direction of gravity, it's compression only. So it's great for creating shapes of vaults. And let's check it out in 2D. Let's see a vault being formed using this script. So I'm just gonna go here, and again let's explain what do we see here. This time it's not a single line, it's a grid of points and lines, and this time we're gonna again do the same thing. Actually, we're gonna apply some vector force to everything. We're gonna take the lines in one direction, the other direction, make the little segments, right, interconnect everything in here, and the last thing we need is the 4 corner points. That's still the same thing as we had before. The only thing I added now is in here, and that's whenever I generate these springs, these little lines, I'm actually gonna ask the simulation to try to stretch, try to make every single line over here smaller a little bit. It's just 80%, but we're gonna see that this behavior is something we already seen somewhere before. So I'm going to turn on my preview, and let's just forget about these diagonals. I'm gonna talk about them in a moment. And if I make this simulation run, you can see that everything is trying to stretch. I can exaggerate this a little bit. We can see that we have something which to me resembles a membrane. If you look from top, we can see these nice shapes, and it's just a membrane. But then we can apply the gravitation. So remember, we had the points, and on these points we have some vectors, right? And that means we can, when those vectors are bigger, we can try to make a vault out of this. So if I apply this, when this is 0, it's just a membrane. But when I apply some gravitation to it, we can actually get back with the stretching, and we can see a nice catenary vault. And this shape is exactly like we've seen before. Sorry, go back to full screen. And that's quite okay. We have catenaries in this direction even in the other direction. And the funny thing about this simulation here is I can try to get these corners closer to each other and see what happens with the structure. And I can play with this and can see what happens when I get them too close. It's just a piece of cloth and it gets almost like that. And I can just go back and see how that structure behaves. There's one more thing I wanted to show here, and that's this opportunity to interact with it. So when I apply some force to it, I can just take my mouse here and drag a piece of that construction and see how would it react to some external forces. And since it's very interactive like this, I can really see what I'm designing before I start cutting some wood or some other structures. And again, it's still the same for the membrane. So if I just drop the gravitation like it is, and I can start dragging some points and see how would a really heavy membrane look like. I can start stretching the membrane and see what would happen if this was a shape I was going to model. So it's very playful, and I can see what would happen if the constraints for this construction were different. Okay, cool. So we have this amazing tool, just a few goal objects for the simulation, and we can model nice walls, and we can model nice membranes, and it looks quite powerful, right? So I'm just gonna hide this and get back to my presentation, and I'm gonna ask a question here. Can we use the same method for the grid shell? Because it, like, to some people it might look like it's a it's a wall kind of thing. It's made from little pieces. It might be the same, right? So when we talk about grid shell, it's usually some spatially, usually double curved framework of rods. It has some joints, right? And usually we construct these things lying on a floor, and by pre-stressing the constraints or the anchor points, like usually applying some cable and pushing the supports closer together, we get this nice shape, which is usually a dome-like thing. So let's use the same approach here, right? So again, a grid shell is usually consisting of two systems, like one going in one direction, the other one going in the other direction. It can form different shapes, so I'm going to keep it to the grid so we can compare it to the previous thing we had. So again, let's jump back to our scripting environment. I'm going to start with a simple grid. I mean, not grid, I mean grid shell rod. So let's turn on the preview. It's just a line again. It's going to be very similar to what we saw in the beginning. Again, we have 2 points, right? Then there's a line, and we can divide that line into many points again. But this time we are just going to create a polyline. It is segmented, but it's one object only. It's a linear curve with many segments, and we're gonna use a different goal for this. It's actually a spring, but this time it's named rod, and it has this axial strength and bend strength. That means that as you have the polyline with many points, in every single point in there, there can be some kind of bending, and there's a lot of force in there. And this time, there's going to be a little difference that we have a lot of points, right? And vector is actually going to be only on one of them. We can imagine we have a crane and we are lifting up this structure over here. This is how it's usually constructed. So we're just lifting it up at one point only. And the rest is the same. We have these 2 points as as anchor points, and the last thing we need is actually something to pre-stress the bending polyline. So we're going to create just a single line out of these 2 points, and you know, this line can then, using the slider, it can shrink, and that's gonna give us more bending in the structure. So I'm gonna start with number 0 in there, just a little bit of push from here, and let's see how does this work. So we have this blue line, and I'm gonna start the simulation. You can see that it starts going up slightly. It's bending, but you know, there's not much room because we are actually, you know, it's getting longer, so we are putting some stress in there. But once I start shortening the bottom line, we can see some cool shape emerge. Again, it's just one shape like this. It's 2D, but we can see that this might be a good shape for a grid shell. So basically, let's look at this situation. So, now we're in 2D, and what happens when we put, you know, many more next to each other and we connect them? So this is a simple one rod, and let's have a look at the grid shell as a 2D structure. So again, I'm gonna quickly explain what are we looking at. This script over here, again, we're starting with a grid. Of course, we can change the size of it, we can change the amount of things in here for the sake of you know, this streaming, or I mean, for the sake of recording, I'm just gonna keep it to simple 12 times 12, but we can go crazy with this. We're gonna pick a point to support all these things. This time it's gonna be a point in the middle. Let's see, and we're gonna apply some force to it. That's similar to what we had before. Then we need to do the same thing with the lines. So before we had one line as a polyline consisting out of, you know, many points. So in one direction, another direction, and these are going to be the rods. So again, it's a spring, but this one can bend. And the last thing we need is anchor points at the edges, of course. And then we're gonna, you know, need some pre-stressors. These are the cables which are going to be used to put the anchor points closer to each other to introduce more bending into the whole structure as I move this slider over here to less than 1. So I guess it's quite similar to the situation before. Let's go to the normal preview here like this, and let's make it run. So I'm gonna start the simulation here. By default, we could see that, you know, there's a little bit of bending, and since all these beams or rods, I mean, they are bending as well, there's the 1 point for, you know, lifting up is just enough. It's okay. And this looks almost similar to the previous example, but when we look from the top, it's still like kind of squarish. And the funny things start to happen when we start to use the pre-stressors. So I'm just gonna get this nice view, and I'm gonna slowly get the anchors closer to each other. And since this time we have bending in the system, from the top view it looks totally differently than the previous tension only or compression only structure. And we have these nice parts where there's a lot of bending, and you know, some parts where the bending is not so hard. And the funny thing about this is when I get back to the initial position, and I'm gonna pick a different point for lifting it up. So I'm just gonna lift it up maybe from this point. I'm gonna apply this simulation again. You can see that initially it looks like this. It's maybe not gonna be symmetrical, but when I get back to lowering this number, we're gonna see some funny thing emerge, and gradually we'll get to the total is the same shape, right? So from the top it looks like this, and like despite a little bit of asymmetricity, because of course we're pulling it over here, it seems like we have the same shape. So the grid shell is quite resistant to other things. This is the shape for this kind of floor plan, right? So this is quite nice, and now it's time to ask a question. What's the difference actually? So I'm gonna go back, and we have grid shells on this side, and we have these compression only things. We can think of membranes as well if they were hanging down. So is it just a catenary curve or not? Well, since you cannot answer me right now, I'm gonna be I'm gonna have to I'm gonna have to go back to my scripting environment and convince you that it's not the same thing. So I'm just gonna restart this, and I'm gonna go back over here and restart this and make it visible as well. So okay, maybe we should have the same size. So I'm gonna use this slider to say that it's 500 exactly. Restart this, and this is gonna be 500 exactly. So we have the same grid now, and let's run this one. And let's run the other one as well. So you can see that the shapes are totally different, even if we look from the top view. The pink one is the tensile only, or if it goes up, it's a compression only. We can see that there's a it's concave looking at it from the top view. And there's one more thing to make it matching. I can try to stretch the anchor points closer to each other over here, and we can see that both constructions react to this action in a very different way, right? So I can play with it a little bit, try to stretch it together, and this is the difference, right? So it's not just catenary curve, it's a whole different behavior. And I believe this is the strong thing about this tool, because we can run around and touch it, play with it, see what does it do when we apply some other forces to it, and this is building our intuition and experience, and that's, I believe, very interesting. Okay, so that's it, and I have one more bonus example, because so far we've been talking about tension only or compression only structures, and also bending active structures when there's moment in the structure, and this tool is actually enabling us to work with both tension and compression together. And a nice example of this would be the tensegrity structure. So we can see that there are some stiff rods which don't bend at all, and they are connected by cables which are working with the tension. And of course the rods are being compressed, right? And they're very good at it, so they don't compress that much. So let's jump back again, and let's see this another example where we are using both types of both types of action in our structure. I'm just going to enable this. We can start with this very simple example. We have 3 rods for the compression, and then we have always 3 cables coming from each end of each one, and it's in this cyclic manner. And this goes up, and this goes up, and this goes up as well. So this is a very simple setup. We can make it run by just double clicking over here, and you can see that the cables start pulling and the rods are resisting the stress, the compression, and that's it. We can have this nice first part of the tower or something like that, and it's still reactive. So I can touch this point and see what happens if I flick this into space, and it's still reacting to my actually questions. I'm just asking, hey, little construction, what would you do if I pushed you over here? And this is quite stable. It's just a triangle, so it might be very useful for something which needs to withstand a lot. But I can get experimental. I can say, hey, why 3? I want 5, and I want it higher. And as soon as I restart my preview, so that we see what we actually set up here, I can make it larger or smaller. I can change the radius. It's still parametric. So let's see how this will work. You can see there's more action here if it's 5, because this one is not connected to this one, so maybe we're breaking some rules here. But this is building my intuition. I can still play with this thing. I can interact with it, and I can learn how such a structure could work. So basically, to sum up, we can model all sorts of structures which are using compression only or tension only, using springs. We can simulate as well bending active structures, something like a grid shell, using springs which can bend on a polyline, and we can do all sorts of combinations of tension and compression as well. As an example, we've chosen the tensegrity structure. So here are some links which might be helpful, because you can download a 90-day evaluation version of this. For students, there are always some kind of discounts, and it's quite awesome. And you can start building your own simulations and learn how these structures work, and get your intuition in here. And I guess that's amazing. So I hope there's going to be some interesting questions on the break. Here are our contact info. We are from the Faculty of Architecture, and I look forward to hear what you want to say about these things. So thank you for your attention.